Welcome to this video. This is video number 6 in my series of videos on Whitehead and Russell's Principia Mathematica. In this video, we'll be looking at section 12, which introduces the axiom of reducibility. The contents of section 12 are effectively two primitive propositions. However, there is some considerable necessary explanation that I'll need to go through before the propositions can really be understood, so I won't be introducing them straight away. The build-up to the statement of the axiom of reducibility will take some time. Without the explanation, then the axiom of reducibility, or maybe I should say axioms of reducibility, won't really make any real sense. The axioms of reducibility themselves will only occupy a small part of this video. I'll need to explain the hierarchy of functions because this hierarchy is not anywhere near as simple as we might hope it to be. But understanding the hierarchy of functions is key to understanding the axiom of reducibility. The derivation of the functional hierarchy is quite complex, and for various reasons it's not the easiest thing to follow and make sense of in Principia Mathematica. I've arrived at an understanding that I find satisfactory, at least, of the functional hierarchy, and my explanation in this video of the hierarchy is going to reflect my own personal understanding of things. So I accept that I might not be 100% correct in everything that I say, and I would welcome any corrections from anyone who has a better understanding of Principia Mathematica than I do. I'll also be taking this opportunity to fill in some gaps and tie up some loose ends that I've necessarily left in previous videos. For example, I've mentioned types several times in previous videos, so I'll be explaining a bit more about types and explaining how the theory of types can be used to resolve certain contradictions that we might come across. I'll also give a brief account of the propositional hierarchy as distinguished from the functional hierarchy. And this will just be a few brief comments because the propositional hierarchy is not of great interest to us, but I have mentioned it a few times already in some previous videos, and it does have a use, but I'd just like to tie up that loose end. So I'm just going to give a brief reminder now about how the theory of types comes about. We could take as our start point Russell's famous paradox, which could be formulated something along the lines of: let W be a class of all those classes which are not members of themselves, then whatever class X may be, X is a W is equivalent to X is not an X. And hence, giving to X the value W, we get W is a W is equivalent to W is not a W, which is a clear contradiction. And other examples are the man who says, I am lying, or a further example might be Burali-Forty's paradox of the ordinal number of the series of all ordinals. And according to Russell, these paradoxes and contradictions, and indeed others of a similar nature, arise when we make reference to an illegitimate totality of some kind, or if we fail to take into consideration that certain words or certain symbols have different meanings in different contexts. As we saw in a previous video, the word false can mean different things. It has different meanings within our system as applied to different kinds of propositions. We can't say anything or make any significant statements about a totality which doesn't exist. And I'm just going to quote now directly from Principia Mathematica. So this is on page 40 of the introduction to the first edition of Principia Mathematica. And it says, the principle which enables us to avoid illegitimate totalities may be stated as follows. Whatever involves all of a collection must not be one of the collection. Or conversely, if provided a certain collection had a total, it would have members only definable in terms of that total, then the said collection has no total. We shall call this the vicious circle principle, because it enables us to avoid the vicious circles involved in the assumption of illegitimate totalities. Whitehead and Russell's solution to these paradoxes and similar paradoxes starts out by forbidding a function, and we usually work with functions, from being amongst its own arguments. So for example, we get things like phi of phi, and these within our system, expressions such as this are just simply meaningless. They can't be judged as true or false, but are just deemed to be simply meaningless. A function is only determined once all of its values are determined, so therefore the function must presuppose its values and not the other way around, and therefore a function cannot presuppose itself. In this way, we find that our function must be of a different kind of object a different type to its arguments. And now if the function is an argument in yet another function, we find that this second function must also be of a different type to the first function, which is also of a different type to the arguments of that first function. How the theory of types resolves the contradictions just mentioned will be explained towards the end of the video. A type is defined as the range of significance of some function, and no type exists that is not the range of significance of some function. We can also have functions as arguments in other functions, which means that functions also form types, potentially. We should understand that functions that have different ranges of significance are necessarily of different types. In particular, we should observe that functions of differing numbers of real variables are of different types. But we shouldn't, however, assume that functions with the same ranges of significance are all going to be of the same type. And this will become much clearer in the example that I'm going to give in a couple of minutes, but even more clear as I go through the derivation of the functional hierarchy. Individuals were defined in section 9 as follows. We say that x is individual if x is neither a proposition nor a function. And individuals form the constituents of elementary propositions. And once we have individuals, then we can start to form functions of individuals. And it would seem that we're able to form a very straightforward, simple hierarchy at this point of individuals, functions of individuals, and functions of individuals. But we're going to have to be very careful here, as the following example is going to show. So let's start out by forming a function of two variables. So f phi z x. Okay, f of phi and x, where x ranges over the totality of individuals, and this variable here, phi, ranges over those functions for which phi x is significant. We can now use a process called generalization to turn one or more of the real variables of this function into apparent variables. So what we're going to do is we're going to turn this real variable phi into an apparent variable, and we write like that. Okay, and just a quick note here. We tend to use just phi instead of what would arguably be strictly more accurate, which would be this. Just for sake of brevity, really, we use this notation here rather than this notation, so I won't typically use that notation. Okay, so now this is a function of one variable, x, because remember that an apparent variable, even though it's called an apparent variable, it's not a variable in the true sense of the word. So if our apparent variable here ranges over all functions phi for which phi x is significant, then it must be that this function is amongst that collection of functions, because this is a function of x and x is in the range of significance of this function. But this is not possible because we already know that a function cannot be amongst its own arguments. So we see then that the apparent variable can't possibly range over all functions phi for which phi x is significant, and the conclusion is therefore that there is no single totality of functions phi for which phi x is significant. Whichever collection of such functions we take, we can always form a new function in this way, using generalization, which cannot be amongst the functions of that collection. If we're going to allow an apparent variable to range over functions phi for which phi x is significant, then we must restrict the range in some suitable way, or alternatively just give up on the idea altogether, which is not really the option that we want to take at this stage. Certainly we'd prefer to find a solution to the problem rather than just give up at the first sign of difficulty. So we're going to have to proceed with a little bit more care in constructing the hierarchy of functions. As we've seen, individuals form the basic first kind or lowest kind of type in our hierarchy. We're going to assume a single totality of individuals moving forward, and of course that our individuals do form a legitimate totality, and therefore we can have apparent variables ranging over the totality of individuals. So now let's start to form functions with individuals as arguments, but which for the time being don't have any apparent variables. So we form functions of the form phi x, phi xy, phi xyz, and any number or any finite number of arguments that we choose, but with the restriction that all of the arguments must range over the totality of individuals. So once we've got these functions, now we can start to generalize some of these real variables, which means to convert some or possibly all of the real variables to apparent variables to form new expressions, possibly new functions. In which case we get things like x, phi xy, xy, phi xyz, where we've generalized some of the real variables to apparent variables, or we could generalize all of the apparent real variables to apparent variables to get x, phi x, xy, phi xy, and so on and so forth. And it's important for us to note here that each node in this diagram, so all of these are represent different and distinct types, and we'll see over the next few minutes or so that it is actually appropriate for me to refer to them as types. Even though it might actually seem that some of these nodes ought to be representing functions of the same type. So for example, if we take phi x and this function here, x phi xy, both of these are functions of a single variable. So here we've got a function of x, here we've got a function of y. Actually, it doesn't make any difference that this is a function of x and this is a function of y, because both of the variables here are ranging over the totality of individuals. So they're both functions of a single argument which ranges over the totality of individuals. However, they must be functions of different types. They can't be of the same type. And the reason for that is the values of this function here, the phi x, are elementary propositions, whereas the values of this function are going to be first order propositions. So we came across first order propositions in the video that I did on section 9, for example. And we can continue this, so we could have, for example, x, y, phi x, y, z. Again, this is a function of one real variable which ranges over the totality of individuals, and the values of this function again are going to be first order propositions, but with two apparent variables here. So that must be of a different type to this, which is first order proposition. The values here are first order propositions of one apparent variable, and the values of this are elementary propositions. So we can see that even though it would seem that these are of the same type, they are actually of different types. And similarly, we might think that these ought to be of the same type, but it turns out that they also are of different types. So each node in the diagram represents a different type. I just need to make a little remark at this stage, something that I just overlooked, that I meant to explain. In each of these nodes, when I've generalized some of the apparent variables, I should have made this clear, but for example, I've used for this node here phi xy always. Included in there are going to be functions of the form phi xy sometimes. So generalization encompasses both of these types of generalization. It's just in the diagram, just to avoid the diagram being too cluttered, I've just always gone for this particular type of generalization. But in each of these categories, really, we've got really two types of generalization that could go on. We've got the always or the sometimes, however you want to refer to it. Okay, so here's some new terminology that we're going to definitely need moving forward. So functions which have no apparent variables and which only take individuals as arguments are called first order matrices. So our first order matrices here are these ones in this first row in the diagram. I don't know if it's clear in the video, but there's a red box around each of these. So note that first order matrices are elementary functions, since once values are assigned to the variables of a first order matrix, we obtain an elementary proposition, but there's no apparent variables there. So they can't be first order propositions, there must be elementary propositions. A function that's either a first order matrix or is obtained from a first order matrix by generalization, so has apparent variables, but still has at least one real variable, which is an individual, is called a first order function. So the first order functions here includes matrices, but also all of these. Again, I don't know if it's clear that these have green boxes around them, but not including these right at the very ends of the columns. These are not first order functions. We'll have a different phrase for these in a second. We can continue the process of generalization to for any finite number of times until all real variables are generalized to apparent variables. And a first order proposition is a proposition obtained from a first order matrix by generalizing all real variables to apparent variables. So these here with the black boxes around them, right at the ends of each of the columns, these are the first order propositions. And it's worth noting that any first order proposition could be obtained from a first order matrix through sufficiently many generalizations. First order matrices are therefore the source of all first order propositions, and we also note that all first order functions are accounted for in this diagram. So there are no first order functions that are neither matrices nor obtainable from matrices by sufficiently many generalizations. We'd like to be able to have first order functions, but not necessarily first order propositions as variables in other functions, but we don't currently have a suitable notation for this. So we're going to use the notation phi exclamation mark to denote a variable first order function of one argument. That argument necessarily ranges over the totality of individuals, and similarly phi exclamation mark x hat y hat to denote a variable first order function of two variables. Again, both arguments necessarily ranging over the totality of individuals, and so on. So we could have any finite number of arguments that we wish, provided that all of the arguments range over the totality of individuals. But we've got a problem though. Because we've got many first order functions of a single variable, as we've already seen, we don't just have one type as we did with individuals. And similarly for any other number of variables, we've always got multiple types to consider. As we've seen, phi x, phi xy, xy, phi xyz are all functions of one variable, but are of different types, and we can't ever have a variable which ranges over more than one type, as I've already mentioned in a previous video, I think. So since our variable can only range over a single type, the question now is which are we going to choose? And to a certain extent, the choice is completely arbitrary. There's no compulsion for us to choose matrices or any other type of first order function of a single variable as the range of phi exclamation mark, and we will for the time being choose phi exclamation mark to range over any appropriate type that we wish, though this doesn't mean that we allow phi exclamation mark to range over all types as if they were all mixed in together. We simply choose the type that we wish phi exclamation mark to range over, and then that variable effectively becomes tied to that particular type. The values of phi exclamation mark are called predicative functions of an individual. So if phi exclamation mark is chosen to range over first order matrices of one variable, then predicative functions of an individual are first order matrices of one variable. If we'd chosen functions of this type as the range of phi exclamation mark, then functions of that particular type would be called predicative functions of an individual. And in this way we see that since our variable can range over any appropriate type, all first order functions of one variable can be called predicative functions of an individual. And in the same way that we've referred to x as an individual, even though it's really an individual which ranges over the totality of individuals, we'll also have the habit of referring to phi exclamation mark itself as a predicative function of an individual, or possibly just predicative function. The values of phi exclamation mark with two variables will be called predicative functions of two individuals, or again we may just refer to phi exclamation mark with two real variables itself as a predicative function of two individuals. But again, we can allow phi exclamation mark with two variables to range over any appropriate fixed type of function that we wish. And we see then that all first order functions are predicative functions of a certain number of variables, all of which range over the totality of individuals. So now we have variables whose respective ranges are first order functions of however many variables we choose, provided that all of those variables range over the totality of individuals. And the ranges of these new variables form legitimate totalities themselves, called predicative functions. So now we have well-defined legitimate totalities of first order functions, and we can start to consider these as the ranges of significance of new functions. And remember that functions presuppose their values or their ranges of significance, so we are justified in using the word type to describe these totalities of functions, these predicative functions. So now let's consider the new functions, f phi exclamation mark, g phi exclamation mark, psi exclamation mark, h phi exclamation mark, x. So this is a function of one variable, this is a function of two variables, and this is also a function of two variables. There's an overwhelming range of possibilities at this stage for the forms of these new functions that we form. When we were forming the first order functions, for example, we just had the single totality of individuals over which all of our variables had to range. The only important thing was the number of variables, effectively. But at this stage, we've got all different possibilities, because not only do we have the totality of individuals to worry about, but we've also got an infinite number of totalities of first order functions that we've got to worry about as well. But in these new functions, what we see is that we've got the variables are either first order functions of some description or individuals. So they've got either first order functions or individuals as their arguments, but there's no apparent variables at this stage. There's no necessity for our new functions to have individuals as arguments, but we need to have at this stage at least one variable which ranges over some totality of first order functions as an argument in these new functions that we're considering. And there will of course always be a finite number of arguments in any function that we consider. So new terminology, a function with no apparent variables and whose arguments are either individuals or first order functions with at least one variable ranging over some totality of first order functions are called second order matrices. And just like with first order matrices, we can start to generalize some of the real variables of the first order matrices. We can do the same with second order matrices. So these are examples of second order matrices because there's no apparent variables in any of these, but I can change some of the real variables to apparent variables. So if we start with the f here, I can convert this real variable to the apparent variable phi. And just a quick point that I need to make here, strictly speaking, I should be writing something like this when I convert this to an apparent variable, but it's conventional. You'll see this in Principia Mathematica. This notation is not used, it's always this notation that's used. So it's an abbreviated notation. So I'm going to stick with that notation because it is more succinct, easier to write. Okay, so moving over to this, I could go for, I could have psi, g, phi, exclamation mark, psi, exclamation mark, or I might go for both real variables converted to apparent variables and get something like that. Over here, I might just convert the individual to an apparent variable and get that, for instance. So there's all different combinations that I can go for. Again, I could also have things like this when I generalize. So there's a huge range of possibilities at this stage. A function that's either a second order matrix or is obtained from a second order matrix by converting some but not all of the real variables to apparent variables through generalization is called a second order function. So in the examples here, these are all second order functions because they're matrices. This would be a second order function, and these two here would also be second order functions. We can continue this generalization process just like we did with first order functions any finite number of times until all real variables are generalized to apparent variables, and a second order proposition is a proposition obtained from a second order matrix by generalizing all real variables to apparent variables. So for example, in this one here, all real variables have been converted to apparent variables. This would be a genuine proposition and it would be a second order proposition. Similarly, this is going to be a second order proposition as well. All of the variables have been converted to apparent variables. So we also see then that just as was the case with first order propositions and functions and matrices, that second order matrices are the source of all second order propositions, and also they are the source of all second order functions as well. So there are no second order functions or propositions which cannot be obtained from from some appropriate second order matrix by sufficiently many appropriate generalizations. So noting the function here, g, we've got two separate variables, both of which range over some totality of first order functions of one variable. There's no reason to suspect at this stage that these variables will range over the same totality. So for example, we could have phi exclamation mark ranging over first order matrices of one variable, in other words, functions of the form phi x. And we could have psi exclamation mark range over functions of the form y phi x y. Both of these are first order functions of one variable, but they're of different types. And it might be that psi exclamation mark ranges over functions of this form, psi exclamation mark ranges over functions of this form. There's no reason to believe that both of these are going to range over the same totality of first order functions. So we want to consider now certain totalities of second order functions as the ranges of variables therefore ranging over totalities of second order functions. So then we can start to form yet more new functions. So functions which have second order functions as variables. So we're going to have to consider a few different cases here, because once we get onto second order functions, we get some behaviors which we didn't encounter when we were just dealing with first order functions. So we use the notation F exclamation mark to denote a variable second order function of one variable, where that one variable ranges over some appropriate totality of first order functions. So as before, we need to make a choice about which type of second order functions this new variable is going to range over. Because we could choose, for example, second order matrices. So functions of this form, or we could choose functions of this form. Both of these are second order types of second order function of one variable, where that variable ranges over a totality of first order functions, but they are different types. So I can choose this to range over this type, or I can choose it to range over this type, or any other appropriate type will suffice. So I've got the same freedom really in my choice here as I did with, for example, phi exclamation mark. So we call the values of this function, the functions in the range of significance of this function, predicative functions of a first order function of one variable, or predicative functions of a first order matrix, if we choose phi exclamation mark to range over matrices. Or we may actually just refer to f exclamation mark itself as a predicative function of a first order function, or if there's no risk of confusion, we might just say predicative function. There are some slight variations in the terminology and the usage of terminology, and I can't guarantee that throughout this video, nor can I guarantee it in Principia Mathematica actually, that the terminology is going to be used entirely consistently and entirely strictly as it should be used. We've always got to take into consideration the context, not just what is being said, but in what context something is being said. And this is one of the reasons why in Principia Mathematica the derivation of the hierarchy of functions is particularly difficult to follow, at least for me it was, because the terminology, as far as I can see, is not used entirely consistently throughout. You really do have to drill into the context in which something is being said in order to figure out exactly what is meant. It is possible to do. I think I've managed successfully to do it, but it took a long time for me to figure it out. But unfortunately, that's how it has to be, really. Otherwise, the terminology gets very fussy and just gets a little bit overwhelming from time to time. So these inconsistencies in terminology are in a way a necessary evil. So I don't really see any way that I can completely avoid it. So we see then that since this can range over any appropriate type, that second order functions of one variable which ranges over an appropriate totality of first order functions are all effectively predicative functions. So now we will use this notation, f exclamation mark, to denote a variable second order function of two variables, one of which ranges over some totality of first order functions of one variable, and where the other variable ranges over the totality of individuals. And we'll call again the values of this variable predicative functions, or we might even refer to f exclamation mark itself as a predicative function. So these predicative functions give rise to some interesting behaviour, some interesting behaviours that we didn't see when we considered first order functions, that I'll just spend a little bit of time now just considering in a bit more detail. So from this we can form the expressions by generalizing some of the variables. We can get things like x f exclamation mark phi x, or we might get phi f exclamation mark phi x. Okay, and now I'll just mention how to interpret these symbols here. So if we assume, for example, that f exclamation mark ranges over the second order functions of the form g of phi x, so second order matrices of this particular form, then this is going to be a value, functions of this form are going to be values of this variable. So therefore this expression is going to be referring to functions of the form x phi, so it's this matrix with the variable corresponding to the individuals. It's generalized, it's converted to an apparent variable, and similarly here this is going to give rise to functions of the form phi g. So in the first case here we get a type of function which is a second order function of one variable. That variable ranges over some appropriate type of some appropriate totality of first order functions of one variable, and we could even possibly see this as being a value of this function, this predicative function here. If we set f exclamation mark to range over an appropriate type of second order function, namely ones of this form, then this will actually be a value of this function. So it may be, it's not forced to be, it depends on what we set f exclamation mark to range over. But this therefore is, this type of function it is going to be a predicative function. Okay, these are going to be predicative functions. However, this is different. This type of function it's still a second order function. It has to be second order because it's got reference to first order functions. It's got an apparent variable which ranges over some totality of first order functions. It's a second order function of one variable, but that one variable, which is x, ranges over the totality of individuals. So we've already seen our diagram of first order functions, all of which have arguments which range over totalities of individuals. This function can't have been amongst any of those types, those first order functions. This is a second order function. So what we see then is that functions of this form are called non-predicative functions. So the reason for that is that if we think about the array of first order functions that we had earlier in the video, we had all of the different types of first order function, and we effectively defined all of these as predicative functions because they can all be, each type of function could be the range of some appropriate variable. So they were all predicative functions, but functions of this type were not there. They were not there amongst those types of first order function. This is a second order function. It couldn't have possibly been there. So therefore, this is not one of those predicative functions, and as such we call it a non-predicative function. And we see in general that if we take any second order function and generalize all of the the variables ranging over first order functions, we'll get a non-predicative function. So we might have something like h of phi exclamation mark psi exclamation mark x y z, and if I generalize these two first order variables here, phi psi, then this will now be a second order function of three variables, but all three variables range over the totality of individuals. So this is going to be a non-predicative function. So we see then that it's possible not only to have different types of first order functions of a single variable, but we also have different order functions of a single variable. Naturally, functions of different orders are also of different types as well. So within first order functions, we've got all the different types of functions of a single variable, which obviously ranges over individuals, but then we've got another level, second order functions of a single variable, which also ranges over the totality of individuals, and we've got many different types of second order function as well. And naturally, functions of different orders are also of different types. So it seemed then that the type of a function is not determined purely by the type or types of its arguments. The types of the arguments of a function alone is not sufficient to determine the order, the type of the function or the order of the function. So just because we have a function of one variable which ranges over the totality of individuals, we can't assume that it's going to be a first order function. It might be a second order function, and as we'll see, it could be a third, fourth, whatever order function as we go forward. So we can continue this process to derive third order matrices, functions and propositions in a completely analogous way. So we would expect then that a third order matrix will be a function which has no apparent variables and which has at least one argument, which is a variable which ranges over some totality of second order functions. And then we can start to generalize the arguments to obtain third order functions and propositions. Of course, we can define variables which range over certain totalities of third order functions, and we can define predicative functions, third order predicative functions. In general, we're going to obtain nth order matrices, functions and propositions in a completely analogous way. Generally speaking, we will find that an nth order matrix is a function with no apparent variables and which contains at least one argument which ranges over at least one variable which ranges over some totality of n-1th order functions. And obviously we can define variables ranging over totalities of nth order functions and predicative functions of any finite order. We can have matrices, functions and propositions of any finite order, but we can't have matrices, functions or propositions of infinite order. So we can go we can continue this process as long as we want, but we're always limited to obviously a finite number of steps. We can't pass to the limit. We know that matrices are always the next greatest order than the highest order occurring amongst its arguments. So a matrix is a function, and it's going to have a finite number of arguments. So if we inspect all of the arguments and we note their orders, then there will be a highest order there amongst the arguments. So the matrix will be the next highest order. It's a function of the next highest order. And because of the way that we've defined our predicative functions, then we find that predicative functions are also of the next greatest order than the highest order occurring amongst its arguments. So we can see then that matrices are always predicative functions, but predicative functions are not always matrices. Okay, That's how things stand at this moment in time, at least, but we're going to refine things as we go along. But just for the time being, we don't have an equivalence between, they're not synonymous. The terms predicative function and matrix, they're not synonymous, although we're going to try to make them synonymous as we go along. The notions predicative function and matrix are taken as primitive ideas. So this is on page 172 of the first edition of Principia Mathematica. And we can see that for a variable x of order n in a function, then for any integer m greater than or equal to 1, we can always create a function of order n plus m, where x is the only variable. So to take a particular case, let's suppose we've got a function f, just a function f of two variables, phi, and let's assume that this is some nth order. So this is some nth order variable ranging over some totality of nth order functions, and this ranges over individuals. Okay, so now if I generalize phi, then because the original function was a matrix, it must have been of order n plus 1. So now I've got an n plus 1th order function of a single variable which ranges over the totality of individuals. So in this way, in general, I could obtain non-predicative functions of any order of an individual, and indeed any variables that I wish, using a similar kind of idea. So generally then, functions which are not of the lowest order compatible with the highest order occurring amongst its arguments is called non-predicative. And a non-predicative function of the nth order can be obtained from a predicative function simply by converting all n-1th order variables to apparent variables, and possibly other variables, provided that there remains at least one real variable in the function. And the problem that we seem to have then is that although we have variables ranging over predicative functions, we seem to miss out non-predicative functions. So we could, if we wanted, define variables which range over these totalities of non-predicative functions as well, of each given order. But this is going to result in just a seemingly unmanageable level of complexity. It's already bad enough, really, that we've got so many different types to choose from as the range of our variables within a given order. So remember, with first order functions, we had the choice with phi exclamation mark, do we choose this type or that type or the other type? This is bad enough, but now to bring different orders of function, it becomes completely unmanageable. But fortunately, there's a couple of things that we can do to simplify things. And the first of those things is the axiom of reducibility. So here we come then to the statement of the axiom of reducibility, or maybe I should say axioms of reducibility, because there would be an axiom of reducibility for each for functions of each finite number of variables. So here we've got an axiom of reducibility for functions of one variable, functions of two variables. There would arguably be separate axioms of reducibility for 3, 4, 5, etc. Numbers of variables. But since we only really work with 1 and 2 variables, functions of 1 and 2 variables, that's where we're going to limit ourselves to. So they both do roughly the same job. The only difference between them is the number of variables involved in the functions. So I'm just going to give a bit of an explanation about what they say. So if we take the first one here, then what this is saying is that for any function of x, of one variable x, and x doesn't have to be an individual, it doesn't have to be ranging over the totality of individuals, it could be of an arbitrary order, then we can always find a predicative function of x which is formally equivalent to the original function. So we're not saying that they're equal. They'll be far from equal functions. We don't really have a notion of a use for a notion of equal functions, only formally equivalent functions. So they certainly won't be equal, they'll be formally equivalent. So in other words, whenever for the values of x for which phi is true, then f exclamation mark x will also be true on exactly the same values of x. And for whichever values of x phi is false, f exclamation mark will be false on exactly the same values of x. And similarly for the two variable case. But again, x and y, not necessarily ranging over totality of individuals. They can be variables of arbitrary, albeit finite orders. They don't necessarily have to be ranging over the same totalities either. So what we see then with this axiom of reducibility is that all of those non-predicative functions which we saw earlier, so functions such as phi exclamation mark x, functions such as this maybe, which we saw was a second order function of one variable x which ranges over totality of individuals. All of these non-predicative functions are formally equivalent to some appropriate predicative function. And since we're only ever interested in truth functions, in other words, functions depending only on the truth values of the arguments, we see that we're able to effectively account for all of these functions that would previously have been, let's say, left out of our considerations, that wouldn't have been accounted for by any of our variables. But the axiom of reducibility actually goes a little bit further than that. It doesn't just account for non-predicative functions. So for example, if I take the variable first order function, phi exclamation mark, and let's say I choose this to range over matrices. So in other words, functions of the form phi x. So functions of one variable ranging over individuals and no apparent variables. Well, it turns out that if I choose a function of this type, so y psi xy, or maybe I chose a function of this type, y z psi xy z, for instance, then effectively, because I've chosen these to be my predicative functions when it comes to this variable at least, then this function, if I consider this as a non-predicative function, then I can say that there is a matrix that is formally equivalent to this function. Or similarly, if I chosen a function of this kind, I can use the axiom of reducibility to say that there must be a function, a matrix function, which is formally equivalent to this function. So what I see, the upshot is then that I can always have my variable functions ranging over matrices. I don't need to actually worry about all of these other types of function. So these are all first order functions of one variable ranging over the totality of individuals, but they are all of different types. But actually, axiom of reducibility tells me it doesn't really matter. Take a function of that type, I can always reduce it to a function of this type. Take a function of that type, I could always reduce it to a function of this type. I could go the other way as well if I wanted to. If I chose these as my predicative functions, then I could say for every function of this type, there will always be a function of this type that it's formally equivalent to. But since matrices seem to be the simplest option, then it would seem to make sense that for me to choose matrices as my ranges of these variable functions. So at this stage then, it seems that I might as well redefine my notion of predicative function to effectively be synonymous with matrices. So from this point forward, really, when we talk about predicative functions of any order, really, we're going to be talking about matrices and not really including functions such as these where we've got generalized variables that are apparent variables. There is, however, something that we just need to briefly consider before we make the full transition to predicative function meaning matrices and nothing else. And that is, if I take a function such as this, f of phi exclamation mark x, so a second order function, let's just say it's a second order function of one variable, which ranges over some totality of first order functions of one variable. Let's suppose in the first instance I'd taken this variable to range over functions of this type. So in other words, first order functions that originally were of two variables, x and y, but with the y changed to an apparent variable. So let's say that this phi exclamation mark is ranging over this totality of functions. So these are the values of this function, of functions of this type, are going to be first order propositions. But I'm saying that I can change this, the range of this variable from these functions to matrices. Well, is that valid? Because the values of matrices are elementary propositions. The values of these functions are first order propositions. They're different types. So effectively, by changing from this type of function to matrices, I'm changing the type of the arguments. Is that valid? And the answer to that is yes, that is valid, through what we did in section 9 and section 10, particularly section 9, relating to systematic ambiguity. So any logical constants that are being used in this function will automatically change their meanings to fit with the new type of proposition. So if we had logical constants in here, disjunctions, negations, logical products, things like that, relating to first order propositions, if I suddenly replace those first order propositions with appropriate elementary propositions, then these logical connectives, logical constants, will automatically adapt their meaning to fit this new type of proposition. So systematic ambiguity is a very powerful tool which allows me to effectively consider my variables without any problems, allow them to just range over matrices and no other type of function. There is no particular reason other than sake of simplicity, really, to a certain extent, of choosing predicative functions to be the next highest order above the highest level of the arguments, the highest level occurring amongst the arguments. There is nothing inherently wrong with these functions that we've termed non-predicative functions, and there is nothing special about the functions that we've termed predicative functions. We could choose predicative functions to be m levels above the highest level found occurring amongst the arguments. But ultimately we need to decide on an appropriate restriction that will allow us to form apparent variables and which is not too restrictive. And it turns out that choosing predicative functions to be the next highest order above the highest order occurring amongst the arguments seems to do everything we require and is arguably the simplest option available to us. So you can see then that there is a lot of choice involved in what is happening here. We can choose our predicative functions to be the next highest level above the highest level occurring amongst the arguments. We can choose our predicative functions to just be matrices. These seem to be the simplest options available to us, but we should never, strictly speaking, feel compelled to take this simplest option. The truth is that there is no absolute notion of predicative function. There is a lot of relativity in this system that we've come to develop and accept. We've already seen some of that relative nature of the system, but we can go even further than that. We don't even need a notion of absolute level in our hierarchy. We only need to know the relative levels of the functions involved in our hierarchy. So let's say, for example, we've got a variable function which ranges over some totality of nth order objects, and then another function g exclamation mark y which ranges over some n plus mth order type. Well, I can just reduce the order of everything by n. Okay, so rather than thinking of x ranging over an nth order type, I just think of x as ranging over individuals. And rather than thinking of y as ranging over an n plus mth order type, it's now ranging over an mth order type. So I've reduced everything by n. So in other words, f exclamation mark x, rather than thinking about it as an n plus 1th order function, it's now a first order function. And rather than thinking of g exclamation mark as an n plus m plus 1th order function, it's now just an m plus 1th order function. And since we can go even further than that, because we're only ever interested in predicative functions, which are the next greatest order above the highest order occurring amongst the arguments. Then suppose we've got a variable function, f exclamation mark, and there might be several variables involved in this. But so it has a particular range of significance. Well, all I do is I just define that range of significance as my totality of individuals. Okay, so this becomes the range of significance here becomes my new totality of individuals. And therefore, f exclamation mark just becomes a predicative function, a predicative first order function, first order matrix, in other words. So this, of course, is an immense simplification. If I carry all of this stuff through and take advantage of all of this relativity involved in the system, I can get some massive simplifications involved. So this completes the derivation of the hierarchy of functions. There is just one thing that I want to mention before I just move on to the next part of the video. From time to time we will want to refer to a function of an undetermined order relative to its arguments or arguments. So although we will usually be concerned with predicative functions, from time to time we might just need to consider functions that are potentially not necessarily predicative functions. So for example, we'll just use the notation phi x or something similar to indicate a function that is of an to a certain extent undetermined order relative to its arguments. Now, if I use this notation, because the order is undetermined, I cannot convert this. If this occurs as a variable in any function, I cannot convert it to an apparent variable until I've fixed the order of the function involved. Okay, so remember, if I change a real variable to an apparent variable, I can only do that when I've got a suitable totality of functions over which the apparent variable is ranging. So I can't just have a function of undetermined order and have an apparent variable ranging over functions of undetermined orders. It just doesn't work. So I would have to fix the order in advance. The axiom of reducibility is something that's coming for some serious criticism by various philosophers, logicians and mathematicians, particularly over the decades immediately following the publication of Principia Mathematica. Frank Ramsey, Willard van Orman Quine and Wittgenstein, I believe, have all expressed at various times doubts or concerns about the axiom of reducibility. In particular, Frank Ramsey considered the axiom of reducibility to be not a purely logical principle. Now, why would that be significant? Well, bearing in mind that Whitehead and Russell were initially trying to achieve a complete reduction of classical mathematics to purely logical principles, then if they've actually reduced to some principles that actually include some principles that are not purely logical, then it doesn't seem that however hard they work that they're actually going to achieve their goal. Now, this is kind of subjective. Whether the axiom of reducibility is a purely logical principle or whether it's not, whether it should be accepted, whether it shouldn't be accepted, is in a sense subjective. Okay, so evidently Whitehead and Russell, at least at the time of writing the first edition of Principia Mathematica, found the axiom of reducibility to be a satisfactory principle. I'm not sure about further down the line whether they maintained that stance further down the line. But as we go forwards with Principia Mathematica in this series of videos, I will be accepting the axiom of reducibility as a purely logical principle. So I'm not going to say really anymore. I'm not going to discuss any further in this series of videos whether the axiom of reducibility is or is not a purely logical principle, although I might make a video on that at some point. I've got no intention to do it in the immediate foreseeable future. So now I'm just going to give a brief account of the propositional hierarchy, and I'm only just going to touch on this really because I've mentioned it a couple of times in some previous videos. So the propositional hierarchy can be derived, as far as I can tell, at least, in a similar way to the functional hierarchy. So Principia Mathematica only contains a few scanty details relating to the propositional hierarchy, and I haven't personally gone through all of the details of the derivation of the propositional hierarchy, though I've got a basic idea of how I imagine it's going to go. So whereas with functional hierarchy we start with individuals and form functions of individuals, and then functions of individuals and individuals, and then etc, etc. With the propositional hierarchy we'd start with elementary functions and then effectively first order propositions of different types, and then second order propositions of different types, and this would generate our propositional hierarchy. Since we can obtain propositions from matrices in the functional hierarchy by turning all real variables of a matrix into apparent variables, it turns out that the propositional hierarchy can be derived from the functional hierarchy. Whether the opposite is true, I haven't really investigated, but it turns out anyway that the propositional hierarchy is never actually needed in what is covered in Principia Mathematica. Its only use really is as a thing that can be constructed and which will provide a solution to certain paradoxes and contradictions. The functional hierarchy does everything that we need and want it to do. So we saw in the video for section 9 that the propositional hierarchy has a problem concerning ambiguity of logical constants and logical connectors and things like true and false and systematic ambiguity, in other words. Since the propositional hierarchy is effectively part of the functional hierarchy, then we see that the same problem is present in the functional hierarchy as well. But we've already resolved this problem though in the videos section 9 and section 10. Notice in our derivation of the functional hierarchy, we never actually bothered to introduce variables ranging over propositions in the derivation. Why is this? Well, there's no definitive answer to this, but I suspect it's because to do so would introduce some unnecessary complication. Bearing in mind that we never actually need propositions as variables, what we have, our current functional hierarchy does everything that we need, so we don't really need propositions as variables. So in that case, why bother with them? Since propositions form types, it would seem that they could be the range of significance of certain functions, that we could have variables ranging over these collections of propositions, but really, why complicate things? Things are already complicated enough. Why complicate them? Why complicate them even further? So the upshot is that the propositional hierarchy is useful as something which can be. It can be constructed if we can be bothered to do so in order to solve certain paradoxes. It's also somewhat easier to explain certain things such as systematic ambiguity, as I did in the video for section 9, when referring to the propositional hierarchy rather than the functional hierarchy, but that's really as far as it needs to go for us. Other things that might be worth considering in relation to the decision to go for the functional hierarchy rather than propositional hierarchy are maybe some of the following. So whether these points are relevant or not, I'm going to leave as an open question at this stage. But according to Whitehead and Russell, propositions are what are known as incomplete symbols. They don't, in inverted commas, exist of their own account, but have meaning only in context. They don't exist in the same way, again, inverted commas exist, in the same way that individuals are assumed to have objective existence, in a certain sense at least. So it would seem that to build a theory based on propositions can effectively only ever be hypothetical, especially if you are of the sympathetic to Whitehead and Russell's viewpoints on propositions as incomplete symbols. Individuals, on the other hand, are assumed to exist of their own account, and so to build a hierarchy on these individuals seems to give a much more certain, solid foundation than to build a hierarchy based on propositions. But it also seems that propositions are not indivisible. Individuals are evidently simpler objects than the propositions that they form part of. So since we would like to reduce things to the simplest objects possible, then it stands to reason that propositions wouldn't really do this job. Individuals do a much better job in that respect. Finally then, we come to how all of this can be used to solve the paradoxes and contradictions of the vicious circle type. So I'm just going to give one example of this, which is the case of the man who says, "I am lying." And the problem seems to be that if whoever made this utterance is indeed lying, then they must be telling the truth. And if they're telling the truth, then they must be lying. And here is the solution, according to Whitehead and Russell, to this problem. We can interpret this utterance, "I am lying," as something like the proposition P, which I assert is false. And the problem stems from the assumption that the proposition P, which I assert is false, is amongst the propositions P. And also it seems to stem from, the problem seems to stem from a failure to acknowledge the difference in the meanings of words like true and false as applied to different types of propositions, as we saw in the video to section 9. But we see, however, that the proposition P, which I assert is false, can only be legitimately made about a presupposed totality of propositions, of which P is among the propositions of this totality, but the proposition P, which I assert is false, is not amongst this totality. It is indeed a proposition of a different, higher order than any of the P's. So here we're using the propositional hierarchy to resolve this problem. So the words true and false will have different meanings when applied to P as when they are applied to the proposition P, which I assert is false. So whoever says the proposition P, which I assert is false, must be making a statement about a well-defined collection of propositions, and the proposition P, which I assert is false, is not amongst them. So if P is true, then the statement, the proposition P, which I assert is false, is simply false. And if P is false, then the proposition P, which I assert is false, is simply true. And that's the end of it. There is no contradiction or vicious circle involved. And other paradoxes of the vicious circle type have their solutions rooted in the theory of types. So some of the paradoxes, Burali-Forty's paradox, for example, will need more attention than others to provide a complete and satisfactory solution. I'm not necessarily saying that the solution that I've given to this problem is completely satisfactory at this stage. It might require some details to be fleshed out, but the idea is there in the theory of types. And according to Whitehead and Russell, the theory of types is the key to solving all of the contradictions and paradoxes of the vicious circle type. So that brings us to the end of this rather intense video, I guess. In the next video, I'm going to be looking at, hopefully, both of sections 13 and sections 14. So I'm going to say thank you for watching this video, and I look forward to seeing you in the next video.